So I have to establish this existence of roots of real numbers. And the second thing that we have to introduce is the concept, I will write it in a broad way. The introduction to point set topology of far set of real numbers. First, let me give a theorem which establishes the existence of roots of real numbers. And the theorem goes like that: if you have a real number and n is a natural number greater than or equal to 2, integer, then we have the following thing. If a is non-negative and n is even, then this equation b power n equals to a has a unique solution, say b, and this solution is also non-negative. And whereas in case of n being an odd number, then again there is a solution to this equation. There exists a unique real number b in R which satisfies this equation. So okay, this is all we have to establish. And remember, whenever we will have this existence part completed, and this b will satisfy this equation, then in that case the solution, this b, is known as the nth root of a, and is usually written as, given this notation, since it is a unique, we will give it a notation, this nth root of a, or a power 1 by n. And with this, actually this theorem, we are also able to define the rational powers of real numbers. Okay, let's move to establish the proof of this theorem. And what this proof says, first note that if you have a to be equal to 0, then clearly uh, b equal to 0 is a unique solution. Or I will just rewrite that is the required solution, because for no other real number the nth power is equal to 0. So 0 is the only solution of this equation. And first we establish the theorem for a being non-negative, and for 0 it's done. Next, let's take a to be strictly greater than 0, and then we establish this existence of this, what do you say, solution of this equation. So let's define a set S as set of those real numbers whose nth power do not exceed a. It do not exceed a. Then actually, such a set is something whose supremum of this set is going to be equal to some number b, and the power of the supremum of this set will be equal to a. But this is something that we need to establish. For that, what we need to do the following steps. First, we need to show that the set S is non-empty, and then after that we require to establish that S is bounded from above, because that is something where we will apply the completeness axiom, and that completeness axiom will help us to establish that supremum of S exists, and then finally we have to establish that that supremum being multiplied with itself n times equals A, and that is the required solution. So we first establish that S is non-empty and it is bounded from above, and this non-emptiness is being will be established through using Archimedean property. So how we are going to establish this? I'm going since A is a positive number, so I'm going to use the Archimedean property on the number A and 1. So by Archimedean property, we there is some natural number n such that m times e becomes larger than 1. We are applying Archimedean property on a and 1, and that reciprocal of m is less than a. Now, obviously, m is a positive number, so its reciprocal is also positive. And since 1 by m being a number which is less than 1, so this its power 1 by m to power n is also going to be smaller than less than or equal to 1 by m, and this is less than a. So now we have a number 1 by m whose nth power is less than n, and hence it qualifies to be an element of set S, and thence by the definition of S, set S, it follows that this element 1 by m is an element of S, and so hence the set S is a non-empty set. So it's done. So next we have to talk about the boundedness of this set from above, and let's take a look at this observation, which will let us to establish that this set is bounded from above. Let us take uh, some y to be an element of a real number such that nth power of y is greater than a. So there will be certain, obviously, such numbers will always exist there. And now, if you have such a number whose nth power is strictly greater than a, then I'm going to uh, prove that this y is a upper bound for s. Then y is an upper bound for s. Suppose not. Suppose that y is not an upper bound. Is not an upper bound of s. So what happens? Then, if it is not an upper bound, that means there is some element in s which is not less than or equal to y. That means such a number is obviously greater than y. So then there is some element in S such that x is strictly greater than y. What it implies that then the power of x is always going to be greater than y to power n. We are multiplying x with itself, so we will have this preservation of the multiplication in case of positive numbers, and y being a positive, so x is also a positive number because set has positive numbers. And but y to power n is greater than a, and this implies that x is an element of s whose power is greater than a, and also since x being an element of s means x to power n is less than or equal to a, this is a contradiction. Hence this is a contradiction, and so it proves that this y is an upper bound. This leads us to say that Y being an upper bound means that S is bounded from above. So now it is a bounded from above set and it's a non-empty set, and hence by the axiom of completeness, axiom of completeness, supremum of set X as exists, and let that supremum be denoted by B, and it exists. So it's done now. The existence of supremum is done. Now the only part that that remains to establish is that the power of this number b to power n is equal to a. And also clearly you noted that since 1 by m, we show that 1 by m belongs to S and 1 by m was a positive number. So b has to be greater than or equal to such 1 by m, and therefore b is a positive number. So now we have to establish it. How are we going to establish this thing? We are going to uh, we rule out that b to power n. We are going to rule out these possibilities one by one, because if you rule out these possibilities, then the only possibility that is left to us is that its power is equal to a. So let's first suppose that first let us suppose that b to power n is less than a, and see then what happens. Now let us first mm, show by binomial expansion uh, for this number b plus 1 by k, where k is any natural number to power n. This is the binomial expansion b to power n plus summation, it is some I from 1 to n, is nci b to power n minus I into 1 by k to power I. Okay, and now note that 1 by k is a number, uh, is a real number, and is less than 1 or equal to 1. Hence, its any power is going to be smaller than 1 by k. So here, this 1 by ki is going to be less than 1 by k, and hence this inequality becomes e to power n plus 1 by k. I take out each 1 by k I to be smaller than 1 by k, and now I can write this inequality as I from 1 to n nci e to power n minus I. Let this obviously this summation part is a positive number, and let this number be denoted by r. So I can write it r upon k plus b to power n. So the inequality that we have now is b plus 1 by k to power n, and this is true for any natural number k greater than or equal to 1. Let note this equation here. Now what I'm going to, I have to recheck some contradiction, and for that I'm going to again take the help from the Archimedean property. And what Archimedean property says, by again Archimedean property, that Archimedean property will be applied on, I'm applying this on b to power n, but now we have b to power n less than a, and I need a positive number. I will apply it on a minus b to power n, and it will be applied on r also. So what it says that there is some natural number k such that k times a minus b to power n is strictly greater than r. And this implies that a minus b power n is strictly greater than r by n, r by k. This implies that a minus b to power n is strictly greater than r by k. And with this estimate, or a kind of upper bound for r by k, We have the from this equation star. From star, we have that a plus 1 by k for this k, that for such k to k equals the k of which the existence comes from the Archimedean property, we have a, a b plus 1 by k to power n is less than, what do you say, it is less than or equal to uh, b to power n plus it is r upon k, and using this bound for r by k which is less than or equal to, I can just write a minus b to power uh, n plus b to power n, and you're left with a only. And finally, you have this number b plus 1 by k, whose nth power is less than or equal to k, and implies this implies that this element, by definition of S, is an element of S. How clearly 1 by k is a positive number, b plus 1, uh, clearly b plus 1 by k strictly greater than b. And what is b? B is nothing but supremum of S. And this leads to us, this is a contradiction because you have an element in this set S which is strictly greater than its supremum, which is completely absurd. So this is absurd. Hence, we cannot have this number. We cannot have this number b power n less than a. So this possibility is rolled out now. We don't have this possibility that b power n is possible to be less than a. So the next possibility that we need to rule out is that suppose that b to power n is greater than a. We have to follow the similar lines, and in that case, I'm going to just in that case, what will happen in that case? You use the binomial extension, and you choose any natural number k such that b minus 1 by k to power n. By using again the binomial extension, you will be able to write it to be greater than or equal to b to power n minus some element, positive element t upon r. And then again, by an application of Archimedean property, by an application of Archimedean property, we will be able to find natural number for which we will have bn minus a times k. Sorry, it will be t upon k. This being strictly greater than t, and this will actually imply that minus t upon k will be strictly greater than bn minus a. And plugging in this estimate here, then we will get b to power n minus t upon k is strictly greater than b to power n. So it is minus here, it is a plus here because you are multiplying both sides by minus, and it is b to power n minus b to power n plus a. And hence we have this number b power n minus t by k is greater than a. And from this equation, let it be double star, we have this equation b minus 1 by k power n being greater than or equal to a. And again, by the definition of it, will follow that b minus 1 by k is an element of S. But at the beginning, when we had to show that S is a bounded at outside, we had seen that any number, no, it doesn't belong to S. Sorry, this doesn't prove that it belongs to S. But what it proves that this element b minus 1 by k is an upper bound upper bound for s. But b minus 1 by k is what? What is this number? This number is less than b. How this is possible? There we have an upper bound which is strictly smaller than a is supremum. This is again a contradiction. This is again a contradiction. Hence, this possibility of b power n being greater than a is also ruled out with this computation. And so this proves that b to power n is equal to a. And this proves our claim. This was our claim. This proves our claim. So this was the existence part when a was greater than 0. Next, if you assume that in case of odd powers a less than 0, then I will apply the above argument to minus a, then minus a becomes positive number. Then from above argument, there is a unique uh, positive number b naught such that b naught to power n is equal to minus a. And multiplying it both sides by minus 1 to power n, b naught to power n, you will be having this minus 1 to power n into minus a. And now here I'm going to have the effect of n being odd number is being utilized, that in case of odd number minus 1 to power n is again minus, and minus and minus being multiplied, you are left with only a, and here you will have minus b naught to power n. And hence we see that b equals to minus b naught uh, is unique real number, unique element in R which satisfies, for which we have its power being equal to a. And the proof. Why it is a unique? Because b naught is a unique, and hence it proves that a has a unique nth root. The nth root of a is unique in case of odd number. Now, the only thing that I want to tell you is the difference, that why we are taking a to be positive, a to be non-negative in case of even powers. And the reason is this equation. Look at this equation. I will just write this as a remark, or it must be a note, that in case a is less than 0 and n is even, then b to power n equals a has no solution. It has no solution in R. For example, you look at, you take a to be equal to minus 2, and you take n, since being n, it is a even number, it has to be up from b. And then this equation I can write it as b power m square equals to minus 2. Now on the left hand side, this is a square of some number. This is a square, and square, square of a number is always greater than equal to 0. And then how it can be equal to some negative number? Minus 2 is a negative number. So positive number equal to negative number. This is not possible. It is not possible here. Hence, therefore, we do not have a solution in this. And that's why in case of even powers, a has to be positive. Only positive real numbers with even powers have their nth roots, and whereas for odd powers, it hardly matters whether you are taking positive or negative number.